Design, Development, and FEA of 3-point Actuated Digging and Conveyor System 4. Self-propelled Onion Harvester. Abstract: India is the second largest producer of onions in the world next to China. But the productivity of onions in India is very low, i.e. 14.21 tons/ha. There is a huge requirement of manpower and time, as harvesting of onions is a rigorous work. Our motive being to conceive, design, fabricate and develop 3-point actuated self-propelled onion harvester, i.e. to develop a mechanized technique for onion harvesting which can run on vehicle power supply and won't require any other external power source. This system will have better performance in terms of productivity, fuel economy, operator comfort, and reduce the damage to crops, human fatigue, and time. There are majorly two systems working simultaneously, which are the digging system to loosen the soil and get the onion bulbs out without damaging, and conveying system that conveys the onion bulbs. Various factors are considered for designing, such as type of soil, depth of onion bulbs, size of onion bulbs and damage to onion bulbs. Keywords: 1. 3-point actuator system. 2. Self-propelled. 3. Less damage to onion bulbs. 4. Productivity. 5. FEA analysis. Introduction. Digging system scoops into the soil and pushes the onions and soil mass onto the conveying and windrowing system. This system loosens the soil and gets the onion bulbs out without damaging the onion. It consists of a trapezoidal scoop and V-shaped digging blade designed based on draft acting on it while harvesting the onion. Conveying system was designed such that while the onion bulbs are segregated from soil mass while being conveyed at the end, to a predetermined height. The 3-point actuation system was designed to vary the digging depth of the system considering the variations in soil and onion bulb depth. 2. Digging system. A digging scoop. The digging scoop is a trapezoidal unit consisting of 10 evenly spaced blades. A brief study on onions led us to conclude that the average onion bulb diameter is around 60 mm. Hence, we selected out depth of digging operation as 80 mm, ensuring that the onion doesn't get damaged. These factors were considered to design the digging scoop. 1. Shape and shape factor. Onions can be considered as oblate or prolate. The coefficient of static friction on mild steel for onion plant is equal to the tan of angle of static friction. Coefficient of static friction equals tan. Where is the angle of static friction? 4. Crushing resistance of onion bulb. The resistance of onion bulbs to deform or crush due to force applied upon them is called as the crushing resistance of onion bulb. 5. Bulk density of soil. It is defined as the mass of the dry soil per unit volume denoted by P. 6. Cohesion and angle of internal friction. Cohesion is the property of materials to stick together to the same material. Angle of cohesion is found from the following equation, where PP equals passive resistance of soil acting at angle of soil metal friction with the normal to interface, kg/m, equals bulk density of soil, kg/m2. Z1 equals depth of operation, m. Ca equals soil interaction adhesion, kg/m2. Q equals surcharge pressure on soil from surface above the failure plane, kg/m2. N, Nc, Nq, and Nca are the dimensionless less factor. These are the function of angle of shearing resistance of soil, F, angle of soil metal friction, D, and geometry of loaded interface. The corresponding assumptions were made. 1. Average bulk density of soil, i.e. equals 1450 kg/m3. 2. Cohesion of soil, i.e. C equals 30.18 kN/m2. 3. Adhesion of soil can be taken as 0, i.e. Ca equals 0. 4. Friction equals 0, as soil is scouring over the blade. 5. Surcharge of soil equals 0, i.e. Q equals 0. 6. Rake angle of digger blades equals 15 to 25 degree. Hence, equation 1 can be simplified as substituting these values in 2. We obtained the value of PP, which comes out to be 4.02234 kN/m. The total width of the digger scoop was 0.85 m, so we found the effective PP to be 3.419 kN/m. The passive resistance PP was acting at an angle of friction, d, with normal to the interface. Therefore, force component parallel to the digger scoop face. PP1 equals 4.022 times cos, 74.36, equals 1.084 knots. Force component perpendicular to the digger scoop face. PP2 equals 4.022 times cos, 15.64, equals 3.8730 knots. These force components were used to design the digger scoop, and the FEA was also performed. The thickness of the digger scoop was decided by closely studying other agricultural diggers, and a thickness range between 5 mm to 8 mm was obtained. Later, FEA was performed on these models, and the digger scoop with 5 mm thickness was selected. The 5 mm thickness model was lightweight and safe for the operation. A 1x1 mm sheet was laser cut into the required shape, and the blades were given an angle of 2/0 by hydraulic bending. This digger was then bolted to the side support members. FEA analysis of digger scoop. FEA of the digger scoop was performed, and the most optimum design was selected. Scoop iterations of thickness 5 cm, 6 cm, 7 cm, and 8 cm were selected, and the analysis was performed. The analysis included the various factors like equivalent stress, total deflection, and equivalent strain. Loads PP1 and PP2 were applied to the models, and results were obtained. ANSI registered trademark R18.2 version was used. From the above results, the 5 mm thickness model of the digger scoop was selected. The 5 mm thickness model weighed less and could sustain the soil draft load without failing. 3. Conveying system. The conveying system is used to transfer the onions from the digger scoop to the rear outlet of the system. This system consists of 2 EN8 shafts that were designed by ASME standards. A stainless steel honeycomb mesh belt was used to convey the onions. This belt was selected by taking into account the extent of damage different honeycomb belts might cause to the onions and the maximum sustainable load that a belt can bear. The belt mesh spacing was about 3 cm to ensure that the onions don't pass through it. The chain and sprockets were designed to sustain the maximum draft load of the soil and onions. 4. 3-point actuated system. The entire harvester system was made electrically adjustable with the help of 3 linear actuators. The average depth of the onion bulb inside the soil ranges from 6 cm to 8 cm. To achieve maximum efficiency and to reduce the damage caused to the onion bulb, the depth of digging operation could be changed. These actuators were selected on the basis of maximum load capacity. An electronic framework was provided to control the motion of these actuators. The 2 front actuators were used to change the conveyor angle, and all 3 were actuated to achieve height control. This system was powered from the vehicle battery. Conclusions. It is clearly evident that Indian farmers are facing a shortage of labor and efficient farming solutions. There are very less mechanized options in the onion sector. FEA of the digger scoop was performed, and the most optimum and lightweight design was selected. The actuator system was tested and tuned for accurate response. Hence, the 3-point actuated self-propelling onion harvester was designed to modernize this sector and increase the productivity while ensuring minimum damage to the onion crop. 6. Acknowledgements, optional. The author can acknowledge any person and authority in this section. This is not mandatory.